Hello everybody, we are group 37 and our project name is UCF Go. Our group consists of 4 participants, me, Caio Loureiro, Chandler Earp, Jaron Wilson, and Marco Murati. The University of Central Florida is the largest university by enrollment in Florida, hosting classes for over 72,000 students. It has over 2,000 instructional staff and many other employees that utilize its parking services. Now the question is, how does UCF handle that many vehicles every single day? UCF has a total of 7 parking garages for students and employees, each holding from about 1,000 to 2,000 vehicles daily. Finding a parking spot during rush hour can be very complicated, but what's more complicated is remembering where you parked your vehicle after having to pack up your things and rush to class. The birth of our idea came from this problem. Our idea is derived from a shopping mall business model. We would like to save the user's vehicle's location and show it on a map after he or she has parked the car. Our mobile app would connect to each individual parking spot through a QR code, and once scanned by our hardware, it would transmit the data with the user's location. In other words, how does it work? So the user parks, the hardware sensor scans the QR code on the parking spot, and through Bluetooth, the sensor would transfer the data to the user's mobile phone, and the location would be displayed on the app. Our motivation came from wanting to make people's lives easier. We know how much stress students and even staff are under during their daily routine, and this is something that everybody could benefit from. We also loved the idea because of how big of a challenge it was to our group and to our personal development. Our main goal is to help the UCF community by developing an app that is fully functional with user-friendly accurate location and accessible to as many people as possible. We will also design a hardware device with a car detection feature and implement Bluetooth connectivity from the QR scanning device to the user's cell phone. Our engineering requirements are that the app must run on the latest Android mobile operating system version, that the GPS must be able to store the location of the vehicle for at least 24 hours, that the user's personal information must be encrypted on the database using a 128-bit encryption, that the system should be able to detect a car pulling in a spot and make this parking spot unavailable on the app, and that the QR code displayer and vehicle sensor must be at least IPX5, and that the average time for the user to set up their vehicle should not exceed 1 minute. The marketing requirements are that it should run smoothly on the Android device, it should be very easy to use, it should in no way endanger the driver, it should keep the user's personal information safe, and it should be able to endure Florida weather conditions inside of an outdoor structure. In selecting parts, you must balance the trade-offs of different components between engineering and user requirements. Understanding these relationships within a project can help narrow down the design requirements and reach an end solution. Using a house of quality figure is a great way to represent the trade-off matrix between user and engineering requirements. And in this picture is the house of quality matrix for UCF Go. For our project design approach, a lot of things were put into consideration, such as budget, app compatibility, app usability, the sensor and the car size, and the weather.
This is the block diagram for our project design. As you can see, there are two main subsystems, the parking location subsystem and the garage availability subsystem. Starting with the parking location subsystem, this consists of a Raspberry Pi 4 mounted to the user's automobile. The Raspberry Pi is outfitted with a camera to be able to scan a QR code containing location information at the parking spot. This information is transmitted to the user's smartphone via Bluetooth connection. Next is the garage availability subsystem. This is centered around a custom PCB located at the parking spot that connects to a PIR sensor, a power system, and a Wi-Fi module. The PIR sensor is able to detect motion, and when a car parks in the spot, the Wi-Fi module updates a database of garage availability accordingly. From the Android app, the user is able to view both garage availability information and also their parking location. The blocks in this diagram are color-coded to designate which team member is primarily responsible for each aspect of the design. As previously mentioned, the parking location subsystem is designed around the Raspberry Pi 4. The camera we selected to use to scan the QR code is the Raspberry Pi infrared cut camera. This camera is purpose-built to interface with the Raspberry Pi and includes two infrared lights on either side of the camera to enable functionality even in the dark. The QR code will be located at the front of the parking spot, therefore the camera will be mounted to the front of the user's automobile. The information contained in the QR code will be wirelessly transmitted from the Raspberry Pi to the user's smartphone via their shared Bluetooth connection. On the other hand, the garage availability subsystem is designed around a custom printed circuit board. For prototyping the circuit, it was designed on a breadboard utilizing the Texas Instrument MSP430 Launchpad. The circuit has two main components, the HC-SR501 PIR sensor and the ESP8266 Wi-Fi module. The PCB subsystem is mounted in a front-facing position on a given parking spot, enabling the sensor to detect the motion of a car parking and update the database accordingly. Here is the schematic and layout for our printed circuit board design. The PCB was designed using EasyADA and ordered from JLC PCB. We received the PCBs on Wednesday and will be assembling them next week after we receive our final components. The board has two signal layers, 7 components, and measures 35 mm by 25 mm. For the software design, the ESP8266 Wi-Fi module was programmed with a serial to USB converter. It was flashed with C code written in the Arduino IDE to initialize a Wi-Fi connection, wait for the PIR sensor to set off an interrupt, and then send an update to the database. The Raspberry Pi was programmed to read QR codes with a dedicated Python barcode decoding library. The garage availability information is managed with a MySQL database, and the web application is hosted on Microsoft Azure. For the mobile app, Android was selected to be the target operating system for costs and ease of development. Therefore, the mobile application is being created in Android Studio. The QR code in our project needs to convey location information about a given parking spot. In order to achieve this, it's important to understand the standards behind a QR code. A QR code is like a two-dimensional barcode. The amount of information you can store in a given QR code is controlled by the type of characters you want to store. This chart shows the difference between how many characters you can store in a QR code for the 4 different input modes. It follows that the more bits each character occupies, the fewer characters you can fit in a QR code. For our purposes, we will only need alphanumeric characters. QR codes also have built-in error correction algorithms. These are based off of a Reed-Solomon error correction. There are 4 different levels of error correction a QR code can have: low, medium, quartile, and high. The corresponding percentage of restorable data is shown on this chart. For our project, we are aiming for a QR code with the highest level of error correction to accommodate for imperfect alignment with the camera or other objects obscuring the camera. It was important for our project that the QR code is scanned automatically with no action on the user's part. Therefore, we need a small webcam to mount to the front of the vehicle. Given when a car parks, it is generally less than 2 feet from the front of the spot, and within a range of 2 feet laterally, the camera should have an appropriate focal length and focal range to successfully scan the QR code within these tolerances. In order to save the location information contained in the QR code to the user's smartphone, we need some form of wireless communication. Bluetooth is an extremely popular form of wireless communication that operates using ultra-high frequency radio waves. For our purposes, low-energy Bluetooth is extremely efficient at sending small amounts of data. The chart on this slide compares the difference between the three most recent versions of Bluetooth communication. For our project, we will utilize the onboard Bluetooth 5.0 on the Raspberry Pi 4 to communicate the location stored in the QR code to the user's smartphone. Wi-Fi is another extremely popular form of wireless communication. There are many advantages to using Wi-Fi, such as cost, ease of use, and near universal acceptance. This chart compares the four different 802.11 standards, highlighting their frequencies and maximum data rate. In our project, we are using the ESP8266 Wi-Fi module to communicate the garage availability information from the PCB to the database. This slide shows a basic flowchart representing the functionality of our sensor unit. First, the sensor will take a measurement, then it will compare that measurement to the previous measurement. If there is not a significant change, the system will sleep for a designated time before repeating the process. If there is a significant change, the microcontroller will update the occupancy of the parking spot accordingly, and then transmit that information to the database. For our project, we opted to use the PIR sensor HC-SR501. It has two potentiometers on board that you can adjust to control the sensitivity and output timing of the sensor. There is also a jumper that can be repositioned to switch between single trigger mode and repeatable trigger mode. A microcontroller is a component that is used to control electrical devices in an embedded system. A microcontroller can either be a standalone chip or several components on the circuit board acting together. For our project, we need a microcontroller to take input from the sensor, analyze that data, and transmit the information. For prototyping our design as well as testing components, we opted to use the MSP430 due to convenience and familiarity. For our final design, the microcontroller is an ESP8266 onboard the ESP01 Wi-Fi module that will be a part of our PCB.
For this next section of our project, we'll be gearing more towards the software development. To start off with, the mobile application. When deciding what development tool to design our mobile application, we went with Android Studios. This felt like the best option for us, considering our decisive background in Java-based application development, as well as Android being a lot more expensive than iOS development. In the future, if time allows us, we will be converting to applications such as Flutter or React Native to design a application that works with both Android and iOS. This next slide here shows the demo for our mobile app so far. When you first open up the app, you will see on the left here a login or sign up button. When clicking the login or sign up button, you will be able to enter your email and password to log in or email and password to sign up. When signing up, there will be other entries to input, but for the demo, this is what we have set up so far. When successfully logging in, you'll be taken to the middle page, which is the landing page. Within the landing page, there are user settings, Find My Car button, and Show Available Spots. Each of these functionalities will be described in the use case diagram in the next slide. Here, we have the use case diagram. On the left here, the user can start off with signing in or signing up. When they sign up, their information will be saved to the database and will be proceeding to log in. Once coming to the home page, they have three options to choose from. They can either navigate to user settings, Find My Car, or Show Available Spots, which are each located by buttons. For the user setting, they can either change user information, change their basic app display settings, or log out. For the home page, they have the next option is the Find My Car button. When they click the Find My Car button, they will be able to see their car location on the map. When they click the final button, which is Show Available Spots, they will next be given an option to choose what garage they would like. Once they choose their garage, then it pops up the available spots within that garage. The next section will be talking about the database. The database we will be using would be MongoDB, and the database management will be NoSQL. When designing mobile applications, some people like to use SQL or table-based management, but for our application, this doesn't apply. We can simply use JSON files to store different objects within the database, which is used in MongoDB and will be demonstrated in the next slide. This next slide here shows the car locations in the user collection within the database for our mobile app. When clicking on the car locate or the users, you can see that for each object it has their email, their password, first name, and last name, as well as an object ID to distinguish from which. For the next section of our presentation, we'll be discussing the standards implemented for UCF Go. To start off with, we have the QR code standard. This standard was originally written in 2005, but the symbology was revised in 2015. The models on the right here show everything that was discussed in the standard, starting with Model 1, Model 2, Micro QR, iQR, SQRC, and Frame QR. We'll be looking more closely at Model 2 and SQRC in the next slide, but Model 1 was the original model and Model 2 is the updated version of Model 1. A couple of drawbacks that we've taken from the standard are data encoding methods, as well as being able to implement user application parameters. The impact of this standard made us decide on using the Model 2 QR code. Comparing it with the SQRC, which provides a tighter security on who is allowed to use the QR code, this seemed like the better option, considering that we don't want to be selective on who we allow in. The next standard we have is the software unit testing standard, which developed a great groundwork for how we want to test our code. In the diagram below, you can see a flowchart for this. It starts off with isolating sections of our code and writing test cases. Once those test cases are written, we then test that specific part of the code rather than just running the code all together. Once we see that, we look at the logs and fix the bugs, clean up the code, and run it all again until our whole program is properly functioning. Our program is split into two different sections, the PCB programming and the mobile application programming. The PCB programming is going to be connecting directly with the database, in which it will scan the QR code and transmit the signal over the Wi-Fi. And rather than connecting directly with the mobile application, there will be having a middle ground, which is the database. This will be needed tested using the software unit testing multiple times. The final standard we're going to be looking at today is the low rate wireless network standard. This standard goes into specific details about the specifications of wireless communication with low power, sending a small amount of data between two layers, the physical layer and the medium control access sublayer. This is key for our design, considering our PCB will working on a slow amount of power as well as sending a small amount of data over this wireless network. Another key takeaway from this standard is what type of network we are going to be using, which is the star topology network. Looking at the two networks on the bottom, we see the star topology and the peer-to-peer topology. The peer-to-peer topology is a lot more complex than the star topology, as well as not needed for our project, considering our devices don't need to connect with one another and only the main coordinator.
Low-rate wireless network standards. The Institute of Electrical Electronics Engineers has standards for low-rate wireless networks. These standards is IEEE 802.15.4-2020 and is the most current revision of the standard, which has been revised 5 times since it was created. The standards provide specifications for low data rate, low power wireless transmissions between the physical layer and the medium access control sublayer. The side impact of low-rate wireless networks. Due to the nature and hardware of our project, we believe that a star topology network will be more beneficial and less resource consuming to us due to the fact that the sensors in the parking spots are only being active for a short amount of times, making them reduced function nodes. The central layer network device, being the personal area network coordinator, receives a signal from these devices, and this offers a less complex wireless transmission since there is no need for all the nodes to connect to each other, just to the central unit. Economics and time constraints. We believe these are constraints that most students encounter, including us. UCF Go was solely funded by its members. The delivery of some parts took longer than expected, and some even had an increased price due to COVID. Also, we are all in the last semester, trying to graduate and find a job, so we all have other classes, some of us are actively working or having interviews at the moment. Environmental, social, and political constraints. Most of the team meetings were done virtually, either done via Discord voice call, team chat, group chat, or text. The use of the senior design lab was limited, so we tried to adapt by doing most of the work from home. Ethical, health, and safety constraints. Out of everything said during this presentation, our group believes this is the most important area we can touch. Please be safe while driving. Everybody here has probably used a GPS before, so you can use the app to try to find a spot, but try to limit the amount of cell phone use you use while driving. Otherwise, you'll be putting your life and others in danger. Manufacturability and sustainability constraints. Every one of our companies require very low power to use. The MSP430 and PIR sensors are powered on the PCB using the battery with a voltage converter. The Pi needs to be powered by the vehicle so it can read the QR code automatically. So it can either be plugged in the cigarette lighter plug, the car's computer terminal, or directly into the wire in the battery hardwired. No matter which one is used, its power consumption is so low that it does not affect the battery significantly. Project's budget. This is our original project's budget. Since the first semester we started talking about our project, we've been trying to make this project require as little money as possible. However, we realized that the Pi has a lot of peripherals that cost more than we thought. In the budget, we also allocated some money for team meetings or times we had to try to UCF, get supplies, or buy some food for the meetings. Current progress. Our hardware progress is going very smoothly now that we ordered our PCB and the design is almost done. Once we have the PCB, we're able to test our pipe and test that everything is fine. Software development is moving fast. Our database is set, and we're working on the API for the application. Development of the mobile app work is slow as we're working on the hardware and web application at the moment. Plan for successful completion. We believe that for the project to be successful, we must communicate clearly with each other's research past project, since there is plenty of projects that have done a similar thing like us, so we've been trying to analyze them, see what we can improve and we just can't do. Organize and distribute our tasks, work as a team and help each other as needed, since most of us have strengths and weaknesses, or sometimes we might need some more time to work on something, so we are here to support each other, and we set achievable goals and objectives. What went wrong? Obviously, COVID-19. We are 4 of us computer engineering students. We're not very proficient on circuits and electronics, so we needed a lot of research and time for those. So battery sensors and resistors, LEDs, the PIR sensors, we struggled a little bit with those. And when went right, we were very organized. We had informative group meetings. We started early, had good pacing, and good communication. Thank you so much for your time. Hope you all stay safe. And this is all.